Welcome to lecture 4 of our Foundations of Quantum Mechanics lecture series. Before I continue with the story, I thought it's good to have a little recap of where we are. We are, so to speak, going towards Bell's inequalities, but we started the chapter with a little Gedanken experiment that was originally introduced by David Mermin in the 80s that was supposed to show the essence of Bell's inequalities in a way that makes it clear that this essence does not even rely on any knowledge of quantum theory. You don't need to know the Schroedinger equation. Rather, this Gedanken experiment and also Bell's inequalities are supposed to teach us that nature can display very mysterious correlations. They are mysterious in a certain way, which we will try to understand better. And they only occur in some physical settings, and quantum physics will help us to figure out which are these settings. But in order to understand this, you do not need to know quantum theory. And that was the purpose of this little Gedanken experiment and the logic behind it, looking at these statistics. Of course, behind all of that is the promise that I give you at this point that this is not merely an invented Gedanken experiment, but that there are really experiments in the lab these days that are basically a faithful version of this and which display statistics that are as mysterious as the ones that we discussed. Now, good. So once we discussed this, we want to rewind and we want to go back 90 years or so to the beginning of modern quantum physics and understand what were the steps needed to arrive at this. So how did we find out? How did we understand this? And this is really a series of developments. We are currently discussing the first one, which is the famous Einstein-Podolsky-Rosen paper. And then we will come to an insight given by Schroedinger, who coined the term entanglement. Then Mr. Bohm will enter the picture, who had a slight variation of the original Einstein-Podolsky-Rosen Gedanken experiment, which turned out to be very important, this variation. And then will come John Bell. Okay, I'm sorry for this. Can you hear me now? Yes, okay. That's very funny because I certainly did not mute myself. So when did the sound drop? Should I explain this again? The repetition. So the slide. So for this slide, the sound was still okay for the slide that we're currently looking. Yeah, as soon as I changed slides, I see. Okay, good. So, okay, let me start there again. So in 1935, when Einstein-Podolsky-Rosen wrote their paper, I hope we still do have sound now. When they wrote their paper, things like Heisenberg uncertainty relation were already there. And so was the physical interpretation of this. So if you try to measure the position very precisely, you invariably give a random kick to the momentum so that you would never know what had been the initial value of the momentum before your position measurement. So you can measure either position or momentum, but not both at the same time. And you would never learn both simultaneously. And then people like Niels Bohr drew from that the conclusion that you should not even think, not even conceptually, you should think of the position and the momentum as having well-defined values at the same time, unlike classical physics. And as a corollary, you should not even think of trajectories because a trajectory gives you x of t throughout time, from which you could also deduce the velocity and therefore the momentum at any time. But all of this would just lead to contradictions and therefore should be avoided. This was the understanding back at the time. Now, EPR didn't quite buy all of this, and they wanted to construct a situation where you could know, in principle at least, both position and momentum at the same time. Now, if you could construct such a situation, then you could claim reasonably that both position and momentum are there. They are elements of reality, even though quantum physics itself may not tell us their precise values at any given moment in time. And because that is so, quantum mechanics would be found to be an incomplete theory. Incomplete simply meaning that it does not, at least not precisely, describe at any time all the values of all the elements of reality. It's a little bit then like thermodynamics or statistical physics that only makes statistical predictions, but does not make more precise predictions. However, we would know that there is such a more microscopic precise theory beyond it. So the hope was to show something similar for quantum mechanics, that it's still incomplete, and the hope, of course, is then to make it more complete, to replace it by an even more microscopic, better theory. Now, the question is, of course, how do you do this? How can you construct a situation where you would be able to know in principle both position and momentum at the same time? After all, Heisenberg's uncertainty relation formally tells us that this doesn't work, because the wave function cannot be localized both in position and momentum space at the same time. So that's the formal mathematical reason in quantum theory. But also, more than that, physically, we already know that this Heisenberg uncertainty relation has some physical counterpart, where whenever you analyze a situation where you try to measure, say, the position very precisely, then you have to do so, for example, by shining light on an electron, and that will give rise to some random momentum kicks, and so you will destroy the precise value of the momentum. So there are good reasons why you cannot know position and momentum at the same time. Therefore, they had to resort to a trick. And the trick was to use two particles and to establish some correlations between these particles. These correlations will be very useful, because once you have these correlations, then you can make sure that you measure, say, the position of one particle and the momentum of another particle, and you use the correlations in order to infer the position of the second particle. So you are working partially with measurements and partially with the conclusions or the inference you can draw from these measurements about what should be the properties of another particle. So it's a very smart setup. So last time we started discussing this setup, and the first thing, if you want to describe two particles in quantum mechanics, is of course you have to write down a wave function. It's a function of both positions, x1 and x2. And in their case, it's a very simple wave function. It's just the delta function of the difference of coordinates. What this means is that whenever you measure x1 to have a certain value, you can be sure that x2 has exactly the same value. That's what this means. Then, as usual in quantum mechanics, you can also switch your basis. Instead of position basis, you go to the momentum basis. We know this is done by a Fourier transform. So in this case, you could rewrite this wave function just mathematically by an integral over all momenta, e to the I p times the difference in positions. So that's a mathematical equality. That's simply true. Now, each of these terms that looks like a plane wave is actually a product of two plane waves, one relating to the first particle, and another one. So this is the first particle plane wave moving at plus p, and this is the second particle plane wave moving at minus p. So what you learn from this representation is, whenever you measure the momenta of both particles, then you get some random value, of course. This is a superposition of all possible values of p, so this is not determined, but when you measure, you get some value of p, and you get plus p for the momentum of particle 1, whereas you get minus p for the momentum of particle 2. This is always true. And so here we learn that not only had there been a correlation between x1 and x2 that we already knew, but also there is a correlation between p1 and p2. They are not the same, but they are opposite in sign. Okay. So To summarize, x1 equals x2 in any measurement of the positions, p1 equals minus p2 in any measurement of the momenta. And now comes the big trick. The trick is to measure x1 and from that, I will answer the question in a moment, from that deduce the value of x2. And how do we deduce this? Well, we know that if we did measure x2, we would invariably find automatically that it is equal to x1. We know this is always true, so we can as well say this would also now be true. But instead of then actually measuring x2 in order just to confirm this thing that we have always found to be true anyway, in order not to waste our precious measurement on confirming what we know anyway, we actually do measure the momentum of particle number 2. And now we have achieved a funny situation. We know momentum of particle 2 by measurement, by direct measurement, and we know the value of the coordinate of particle 2 by having deduced it from our measurement of the other particle, which, as we have learned before, is actually correlated. So that's very smart. So here's a first question. Why P1 equals minus P2? We do not know about x1 and x2 in the momentum measurement. That's absolutely true. And I also don't claim that this first line, this first representation of the wave function, that we used to predict what would happen in position measurements of both particles. The second line, which is just another formal representation of the same wave function, we used to predict what happens in momentum measurements. Because you look at the second line, it's an integral over all p. You can view the integral as a sum, so it's like a superposition of many contributions. How does each of these contributions look like? Well, it's a product of two plane waves, e to the plus ipx1 and e to the minus ipx2. How do we interpret them? Well, the first one means the momentum of particle 1 is plus p. The second plane wave means the momentum of particle 2 is minus p. So they are always equal but opposite in sign. Whenever I measure the momentum, I will get one or the other of the many different contributions of the many different values of p, but it will always be true that p1 equals minus p2. So that's the logic here. So these two pieces are independent in the logic. So there's one, the first information from the first line is what happens in x measurements on both particles. The second information from the second line is what happens in momentum measurements. Okay. So now you see, this is a very, very smart idea. Why is it so smart? Because yes, we do measure the momentum of particle 2, and we would now be worried, oh, this will perturb our position, let's say. This is true, but we don't care anymore since we have already deduced the value of the position of particle 2. And deducing this value cannot possibly, one would think, cannot possibly have destroyed our momentum, because it's just our prediction, it's just information. It's not something that we actually do to the particle. We have not measured x2, we just have deduced it from the measurement of x1. And the final point of this argument is then you could still worry that this measurement of x1 could do something to particle 2, but if they are very far apart, then there's no interaction. Maybe there's not even time for a light signal to travel from 1 to 2. So there's no way that the measurement of x1 can really scramble anything about the particle number 2. Okay, so that was the argument. Again, there's another question. In what physical situation can you prepare particles where the wave function would be described by such a delta function? Okay, so I can tell you, so let's construct this. In order for, okay, so I should be a little bit careful. In order for this to be true, the easiest way would be to have two particles which have a very strong attractive interaction and then would form something like a molecule, yeah? Then the wave function of these particles is really such that if I plot this wave function as a function of the difference of coordinates, it is strongly peaked around 0 and then falls off rapidly. So that's the wave function, so to speak, of a molecule made of these two particles. And then you can imagine if the interaction is even stronger, then this wave function gets peaked even more, and then it will be exactly what we needed, so to speak, because it approximates a delta function. And all the arguments, so to speak, the arguments are not perfect anymore, and there will be small spreads and uncertainties introduced, but it doesn't kill the whole thing. Okay. Now, you can complain a little bit about what I just drew, because in the final argument I made, I said the measurement, if the particles are very far apart, then the measurement of x1 cannot possibly influence particle 2, and that is true. The problem is that the way the wave function is a little bit set up, of course, means that the particles are not very far apart. It's a delta function, x1 minus x2. They're actually at the same spot. So if you really want to make this locality argument, then it would be much better to have something like x1 minus x2 minus some distance d. So it's more like you have two particles. They are already apart by a long distance d. But then, so to speak, if you measure x1 and measure x2, then if one of them is displaced to the right, also the right one is displaced to the right. If the other one is displaced to the left, also this one is displaced to the left. So one of the ways to do these things, I mean, there are many possible variations of this. One thing though you need in general is, at some point in the past, there have been interactions between the particles. There, I will answer the next question in a moment. In any case, however you set up your wave function, there will have to have been interactions between the particles at some point in the past, and then you will probably want, so these established correlations and establish this type of wave function, one form or another, and then you can bring them apart. Yes, there's a very good question here. Yes, in principle, I would also be happy if I establish a wave function like this, which basically means the center of mass, for some reason, the center of mass of these two particles is located at 0, and that's fine enough. And then I can have, if I now transform into momentum space, I will find P1 equals plus P2, just the signs are interchanged. And that will also be good, yeah? So here I will have x1 equals minus x2 and P1 equals plus P2. The logic still works, but as you correctly point out, in terms of the locality argument, this is slightly better, because then the two particles don't have to be at the exact same spot. Yeah. Okay, so many ways. Interactions will have been involved at some point in the preparation of the wave function, but they are not needed anymore to have this kind of correlated wave function later in time. So that will be a general scheme. Whenever we talk about all these Bell experiments, interactions will have been needed to establish correlations, but then the interactions can be switched off, or the particles go far apart, so the interactions are no longer important, and you still find the correlations in the wave function. Okay, so I want to summarize now what was achieved. So we note the smart trick was that the measurement of x1 cannot possibly perturb x2, at least if they are far enough apart. In other words, we now know by this very clever construction, with certainty even in this idealized case, the values of both position and momentum. And again, the momentum by direct measurement of particle 2, the position by deduction, because we know there are correlations with x1. And so here we have a situation where we can know with certainty even both position and momentum at the same time. It's true, we had to be clever to arrive here, but still. But quantum mechanics, quantum theory, the wave function cannot ever give us the precise values of position and momentum at the same time. And in this sense, then, in their definition, in their language, quantum mechanics would be incomplete. So to summarize, what do EPR do, logically speaking? First, they assume that quantum mechanics actually correctly describes the situation. These were the early days of quantum mechanics. It could have been that 10 years later, someone does an experiment and finds, no, you actually cannot prepare these wave functions, not even approximately, or something funny happens when you try the measurement and so on. So they assume that quantum mechanics correctly describes the results of such experiments on two particles. So that's the first thing they assume. And the second thing they assume is that the measurement of x1 really cannot perturb x2 and p2 if they are far enough apart. In other words, or in their language, there should be no spooky action at a distance. So no influence between particle 1 and particle 2 at large distances. So these are the two assumptions they have. And if these assumptions are true, then by their logic that I just sketched, they would say that quantum mechanics is incomplete. And then there is the hope that you could construct a more complete theory. So this more complete theory would then presumably be able to tell us the detailed trajectories of particles, both position and momentum at the same time. And probably quantum mechanics would then arise from this more detailed description just as an approximate description that only makes statistical predictions. And there is a name that people have given to such theories, even though not EPR. They today would call it hidden variable theories. Now, why hidden? Well, because at least in terms of direct measurement, apparently it's not possible to measure simultaneously at the same particle position and momentum. So in that sense, it's a little bit hidden from our view, but we would still have the conceptual idea that there is an underlying reality where it makes sense to talk of position and momentum. Okay. Okay, so there's a first question again. How large should be the distance? Well, actually, that is not well defined. In the end, when you analyze these things more closely, then you would say, so first of all, I mean, in real experiments, it will depend on the interaction. Maybe you have strong Coulomb interactions, so you should really make sure to make larger distances. Maybe you have very weak van der Waals interactions, which are weak anyway and fall off more strongly with distance. So then you can be closer and still have no such known influence. But then you start to worry about other fields that you haven't yet even discovered, other forces that you don't even know about, yeah? And then the only thing that saves you is basically relativity. So then you must make sure that this influence cannot even have reached the other particle, because you will measure the other particle before a light signal could have traveled from particle 1 to particle 2. So in real experiments, of course, to rule out the known interactions, you look at the interaction and how strong it is and how it falls off with distance, and then you calculate the numbers. But to rule out even more than that, you need to appeal to relativity and make sure that a light signal could not travel from 1 to 2. Okay, now this reasoning of EPR, of course, did not go completely unchallenged. Especially Niels Bohr was not so happy. And I will now try to sketch for you the relatively brief reply that Bohr gave in my own words. I would say their paper is very convincing. Niels Bohr's paper, when you read it, sounds maybe a little bit vague. On the other hand, if you read it then after 80 years later or so, you have to admit that he had a very, very deep understanding of how quantum mechanics really works. So what he said is that you are not allowed to treat the particles separately, even if they are far apart, and that every choice of measurement combinations, like position and momentum or momentum and momentum, corresponds to a different experiment which you should analyze separately. It all sounds a little bit mysterious. Especially this fact that even though they are so far apart and maybe not even a light signal could reach the other particle, still he wants us to always discuss the whole experiment consisting of both measurements at the same time. So each measurement combination, like what I mean by that is x1 and then p2, or maybe x1 and x2, is a separate experiment that should be analyzed on its own. And you should not deduce from one of those experiments, for example, x1 and x2 measurements simultaneously, what you would observe in another experiment. In particular, it's not allowed to deduce what would have been. So what we mean by that is this very important step that we made here. We said we measure x1, then we know from all the other experiments and statistics we collected that if we now would measure x2, we would find x1. Of course, we do not measure x2. We choose to measure p2 instead. That's the trick, the whole trick. But we say, if we would have measured x2, we know already its value. And according to Niels Bohr, this kind of reasoning will turn into trouble, yeah, and therefore it should be avoided. And we now know, indeed, this is the kind of reasoning that spells trouble and that should be avoided. And it's really remarkable that he understood all of this already back at the day. So how did Bohr got this idea? Oh, whoa, now we get a lot of questions. So how did Bohr get this idea of non-separativity? I'm not quite sure, but you know, the measurement is very important for him. And there was always this thinking, even before discussing two particles, that every quantum mechanical experiment, you should describe everything, including the measurement. This is something that in classical physics we do not really need to care about. We describe the dynamics and then yes, maybe someone does a measurement on how the particles are moving, but we do not really talk about the measurement. But here you always have to specify everything, including the measurement setup and what is precisely measured. And then if you describe another measurement setup where instead of measuring position, you measure momentum, it's a completely new analysis, and you should not deduce from one of these settings what happens in the other setting. So this was already kind of understood for a single particle, and he now here just translates it to the situation with two particles. So I think this was his logical step. So now, next question. I am worried about the causality in EPR. If we do not drop the assumption that P2 measurement disturbs X2 anyway, then X1 has to be randomly disturbed as well, or we can no longer have, and X1 has to be randomly disturbed as well, or we can no longer have X1 equals X2. Is this now about going back if we do not drop the assumption that P2 measurement disturbs X2? Why would you think that X1 has to be randomly perturbed? I mean, clearly P1 is perturbed. This is certainly true. We cannot help it. But again, this should not mean anything for particle number 2. And again, if we measure P2, that also means that, so to speak, after the measurement, X2 is perturbed after this measurement, but we don't care any longer because what we were really interested in were, so to speak, the initial values before the measurement. Before you do the P2 measurement, you have not yet perturbed X2, and you were smart and have deduced the value of X2 from the other one. I don't know whether that answers, probably not. P2 measurement disturbs X2, that's precisely correct. So either X1 is perturbed or we do not have X1 equals X2. No, as I just said, this perturbation is, so to speak, something that happens. We cannot avoid it, but we don't care because we are not interested in the value of X2 after the P2 measurement has been done, and surely then X2 has been perturbed. We are interested in the original value of X2, and that is the one we deduce. And does that make sense? Okay, so maybe think about it for a moment. Okay. I go on in the questions. According to this, would it make sense to say that every interacting particle in the universe is governed by a common probability field? In some sense it is, you know, because we have, in this case, psi of x1, x2. In the case of a million particles considered simultaneously, we would have psi of x1, x2, x3, blah, 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 a very long string of arguments. And that, as far as we know, is the proper description of all the particles in the universe. Maybe sometimes this wave function is a product wave function where x1, x2 are somehow independent of x3, x4, x5. So that makes our life simpler, and we can treat them in separation and don't need to track all these arguments. But in general, yes, that's true. And at least it's proven in countless experiments. if you want to make sure that you don't run into contradiction with the experimental results, then you better look into these many particle wave functions, and there has never been a single case where you would then run into contradictions. So now another question, is it assumed that one observer at x1 and one observer at x2 measure the position of particle 1 and momentum of particle 2 simultaneously, such that whatever interaction they have can't travel instantaneously to influence each other? Yes, precisely, you got it precisely. So the way this would be then done, this Gedanken experiment in practice, would be indeed, you wait until the particles are far enough apart, but they are still in this correlated wave function, this one or similar ones. And one of them measures x1, the other measures p2 simultaneously, and there's no chance that a light signal could travel between the two. Good. This conception of the measurement, isn't it more a philosophical view that he applied first and revealed to correspond to reality? I say this because I do not see on which physical basis at the time you could have this argument. I assume you mean Niels Bohr. Well, I guess what he did is apparently Niels Bohr was a very smart guy. So what he did was to kind of summarize all the known both experimental data and conclusions drawn from the theory up to that point. And he had understood from certain other, even simpler Gedanken experiments, that you really run into trouble if you adopt this kind of thinking that classically is completely allowed, that you say, I could have done the other experiment and then I would have measured this one. I chose not to do it, so I haven't confirmed, in this particular case now, I haven't confirmed by measurement that the value is like I say. But since I did so many other control experiments where always x1 equals x2, in this particular case, I don't even need to measure it. Still, I know that the values are equal. So this kind of reasoning is forbidden, and that he learned from other Gedanken experiments. I should add something here. What would have been, there's a word for this. In English, it's called counterfactual reasoning. So that means you draw conclusions about something that could have been. It wasn't because you did something else, but you still say, oh, if I had done otherwise, I would have found this, and therefore I conclude such and such. And what Bohr had apparently understood from all these other Gedanken experiments is that this is extremely dangerous in quantum mechanics. Okay, good. Yeah, so there was a short advertisement for the average wave function. Yes, we will come to that. Good. So I hope now you understand first that their reasoning was very smart. Second, you understand their hope. Their hope was that there would be such an underlying theory which would then finally help to make sense of everything. And you also understand a little bit Bohr's complaint that in quantum mechanics you should precisely not have this kind of reasoning, what would have been if I had done the other experiment and so on. Okay, so now let's go on in the story. That was 1935. Immediately in the same year, Schroedinger pointed out something funny in an article that we hopefully come back to later, which is the article where he also introduced the famous Schroedinger cat. But here it's a little bit more technical. Here he just points out that EPR works because the wave function has a particular structure. And the structure is that there are correlations between the two particles. More precisely, in terms of wave function of two particles, this means this wave function is not a product wave function. So it's not like a product of two individual wave functions. If it were a product, then there would be no correlations between the particles and the whole thing wouldn't go through. And he introduced a name for this. He called such a psi that is not a product, he called this entangled. So in German, the word would be Verschränkung. This is kind of if you take your two hands and put them together and interleave the fingers, then this is Verschränkung, so to speak. Then your hands are somehow together. In the original EPR proposal, why was it considered reasonable to have two distant experimenters making simultaneous measurements? Well, why not? I mean, you can tell them, I don't know what you're worrying about, but you could tell them at a predefined time at 12 o'clock on noon, you make your measurement. Maybe the next question is related. If you say two persons will measure at the same time, is it enough that the time delay between the measurements is smaller than the light to travel the distance? Because from relativity, no. Yes. Okay, yes, you're absolutely right. In order for the argument to go through is, it need not be precisely simultaneous. It's just enough, say, it depends on the distance, obviously. So 30 centimeters corresponds to 1 nanosecond. So if you have 100 times 30 centimeters, then you have 100 nanoseconds time to do these measurements before a light signal can come from 1 to 2. Okay. So this was a first insight, an interesting insight. He didn't fully understand all the implications of this, and there's a lot of modern theory about entangled wave functions, but that was one insight. And then nothing quite happened for some time until something seemingly small happened, but which turned out to be important. And this is when a person called David Bohm, who was one of the assistants of Einstein actually, wrote a textbook on quantum mechanics in 1950. And he introduced for didactical purposes another version of the original EPR experiment. It's a very nice textbook on quantum mechanics. Maybe it doesn't have quite all the modern notation, but I like it very much. So what he tried to make it even simpler. So instead of having position and momentum, how can you make it simpler? Well, mathematically, the Hilbert space for, say, having position and momentum for a free particle, the Hilbert space is still infinite dimensional. It would be easier if the Hilbert space had a smaller dimension. What's the lowest dimensional Hilbert space you can make? Well, that's 2 dimensions. 1 dimension is trivial, there's nothing to do. So 2 dimensions. So what is the physical system that corresponds to a 2-dimensional Hilbert space, which just means there are only 2 basis states? Well, it's a spin, the spin 1/2, say, of an electron. So instead of position and momentum, consider a spin 1/2 particle, and eventually, of course, 2 of them. So the 2 states will be up, so to speak, and down, just like an electron has these 2 states. I will now describe what he was thinking, and then we will make a kind of break because I want to bring everyone on the same page. If you haven't worked a lot with spin, we will repeat some things. But for now, I will just proceed as if you know your spin 1/2 quantum theory. And so the idea is now to measure not position, but let's say the projection of the spin onto the z direction, either up or down. And not measure momentum, but another non-commuting observable, such as the x component of the spin. So this was his insight. One important part is what Schroedinger mentioned, that that the wave function is entangled, not a product wave function. The other important part that people realized about EPR was that you are talking about x and p. They are 2 non-commuting observables, which means they are connected by Heisenberg uncertainty. You cannot measure them both simultaneously. And the same is true for the different components of the spin, Sx, Sy, and Sz. You also cannot measure them simultaneously. So these are the really essential ingredients. And so now what Bohm imagined is you somehow have a source of 2 spin 1/2 particles. One of them is ejected to the left, and I draw a little ball that represents this particle together with a little arrow that represents the spin. But we already know, since we're talking about quantum physics, we should never imagine that this arrow points in one particular direction. It's more complicated than that. And then the other particle goes in the other direction. So maybe its arrow points down, let's say. We will come to the state in a moment. And then you would want to measure these spins. And the way to measure spins is with a Stern-Gerlach apparatus, so having an inhomogeneous magnetic field. The typical way this looks like is like this. You would have one Stern-Gerlach apparatus on one end. And the inhomogeneous magnetic field would pull the spin up or down, depending well, whether it's up or down. And then you would have a Stern-Gerlach apparatus at the other end as well to measure the second spin. So you really carry out a measurement for both of these spins. Okay, fine. Now, just like EPR stated the wave function of the two particles, also now here you have to state what is the wave function. This wave function will not be formulated in positional momentum space, but will be a spin wave function. And in order to make everything become particularly nice, first of all, of course, it has to be an entangled wave function, not a product state, that's clear. And to make it particularly nice, what David Bohm understood is one particular type of wave function is the nicest one, even though others are possible. And what is assumed is a so-called singlet state. Again, when we when we repeat spin, we will say a little bit more about this, but for the moment, I will pretend that you know what this means. And anyway, even if you don't, we can just explicitly write down the wave function. So it consists of two parts. The first part has the first particle in the up state and the second particle in the down state. Okay, that would be a definite state. But that would be boring because it's actually a product state. And all the results of measurements on this state could be easily explained in using classical logic, nothing very mysterious. But then you add another part, or rather you subtract it. And that has the first particle down and the second particle up. Okay, so it looks harmless enough. It just has these two terms superimposed with equal weight, but with a minus sign in between them. Okay, so first thing to notice, this is an entangled state, which is already good because otherwise nothing would work. And now we can ask ourselves, well, what happens if I do measure the first particle? So to be more precise, okay, let's give them numbers. So this is particle 1, particle 2, and we say measure spin 1. Now, whenever you measure a spin, you also have to specify along which axis. Physically, this is given by the orientation of the Stern-Gerlach magnets. So, for example, here this would be a measurement along the z-axis. If you want any other direction, you have to rotate the Stern-Gerlach apparatus. So here we would say, for simplicity, measure spin 1 along the z-axis. And I assume that these two states, when I said up or down, this was already in the z basis, so along the z-axis. Well, so then this becomes quite simple. In a measurement of spin 1, there are only two possibilities. Either it comes out up or it comes out down. Since these two terms have the same prefactor, at least by magnitude, they are equally likely. So it's 50% one, 50% the other. Yeah? So with probability 50%, I will find up. And then according to the rules of quantum physics, the wave function collapses to this term that was actually found. So now I have only the first term. That's the collapse of the wave function. And the 1 over square root of 2 goes away because now 100% of the probability has to be in this term. Or with 50%, I find the other possibility, namely it's down. And then, of course, well, I have to look at the second term, then spin 1 is down, and then by necessity, spin 2 is up. Okay. So this is the situation after the measurement of spin 1. And now we can ask ourselves, okay, now if I do a measurement of spin 2 subsequently afterwards, what will I find? Well, it's already obvious. It's written here. In the first case where spin 1 was up, I will find down. In the second case where spin 1 was down, I will find up. So the subsequent measurement of spin 2 will give me exactly the opposite spin orientation. So for example, down if the spin 1 was up. And so this is really analogous to what happened with the correlations in position and momentum in the original EPR. So you could compare it, well, either to x1 equals x2, but even more nicely, you could compare it to p1 equals minus p2 because they are even opposite in sign. Okay, so that's a good start. There are these correlations, which you also find out in measurements. And we will then see how this feeds into the rest of the story. But I think now would be a good time actually to, so to speak, take a break from this exciting story that started in 1935 and is still developing as we speak, so to speak. And talk a little bit about spin, so everyone is on the same page and we are not losing anyone just because maybe you're a little bit unfamiliar with how spin physics works. I try to keep it relatively short, and we will offer a little exercise actually in a week or so. But now I will just have this kind of excursion. Okay. So now spin in itself is a rather magic thing, but that's not so much the point here. The reasoning does not really depend on this two-level system to be a spin. It was just how David Bohm formulated things. Why we are discussing spin now is, well, that spin 1/2 in particular is the simplest quantum system. And nowadays it's also sometimes known as a qubit for a quantum computer. And so a lot of foundational discussions then resort to the simplest of all systems. So it would be good to know it. So when people started analyzing orbital angular momentum in a hydrogen atom, they found that the orbital angular momentum operator, which is defined like in classical physics, R cross P, so to speak, that this has a very peculiar property, namely the different components of the angular momentum, they do not commute. They have this very funny commutation relation. It's even more difficult than for position and momentum, where the commutator is simply a number. Here, the commutator of two components is another component. Okay, fine. So before I go on, there was still a question, maybe relating to the previous page. Would it be correct to state this as follows? The common wave function of an n-particle system is an equiprobable sum of all possible combinations of their product states. Well, for this particular state, it's an equiprobable combination of two of the product states. Remember that I left out other possible product states, namely up, up, and down, down. Yeah. And one of the outcomes is realized by measurement. The wave function collapses to that specific product state. Yes, roughly speaking, at least in our case, this is true. It's collapsing to one of the two product states. But if, for example, I also had another term, say up 1, up 2, then there would have been two terms that are compatible with the outcome of finding spin 1 in up, namely up, up, and up, down in this case. And then even after the collapse, I would still have a state that is described as a, say, sum of several terms. So the simple rule, more generally speaking, is that a typical, say, entangled many-particle wave function can be written as a superposition of several of these simple product basis states. And if you do a measurement, you have to select all the basis states that are compatible with the measurement outcome. That's it in short. Oh, can you clarify the difference between entanglement and superposition of states? Also very good question. So superposition is something that already happens even for a single particle. And then we never talk about entanglement because it's only a single particle. There can be no correlations between different particles if there's only a single one, but we can already have superposition, say wave packet on the left, wave packet on the right, superimposed and so on. Now, if I now turn to multiple particles, and I choose to write things in terms of a product basis, then indeed the entangled state will look like a superposition of different of these product terms. So that's the relation. So a superposition of multiple product states can be an entangled state. Sometimes it only looks like that, and if you rearrange it, it still becomes a product state, but it can be an entangled state. Okay. So going back to the spin. Now this was a funny thing people observed about angular momentum, and you know that the hydrogen orbitals are classified according to angular momentum, S, P, D, and so on. But from a purely mathematical point of view, there is already a way, there is also representations of, there are operators that you can define on suitable Hilbert spaces that fulfill exactly the same relation, the same so-called algebra. And these Hilbert spaces can have even dimensions in contrast to what happens, say, for this, for the orbital angular momentum, where for the s orbitals, you have only a one-dimensional Hilbert space. For a p orbital, there are 3 p components for the same p orbital, so it's 3 and 5 and so on. You can also have even dimensional Hilbert spaces. And the simplest case is, of course, a two-dimensional Hilbert space, and that's where the spin 1/2 comes in. Now, this could have been just a mathematical curiosity with no relation to real physics, but it then turned out, oh, even a single electron has, curiously enough, an internal angular momentum, so to speak, that is exactly such a spin 1/2. So the formal way to write this is that the S, either X or Y or Z, the components of the spin operator, are equal to h bar half, and that's, so to speak, the dimensional prefactor, times something dimensionless, sigma. And these sigma operators can be explicitly written down, and this is the only ones we need. We don't need higher spin for what we discuss here. And these sigmas are the so-called Pauli matrices. And I will write them down once, so you can always exploit them when we calculate something. So sigma x would be this simple matrix. You know what happens is that if you act sigma x, okay, I should declare what is my basis. That will become clear if I write down sigma z. This is 1, -1, 0, 0. So in other words, the first of these basis states in my notation has sigma z equals +1 here. And the second of these basis states, the one that then in this matrix is in the lower right corner, has -1. So this defines my basis states. My basis states are basis states of sigma z. And sorry, if I now apply sigma x, for example, to the state that would have sigma z equals -1, what I get is actually, if you apply this matrix, the other state. So sigma x flips the state. Sigma z reproduces the state only with a minus sign, depending on which of the basis states you act on. And sigma x flips the state, and then finally sigma y looks like this. Okay, so these are the three famous Pauli matrices. And with that, you can calculate everything you want to know about spin 1/2. So in particular, eigenstates of the different spin operators. So for example, sigma z applied to 1, 0 is just the same. It's just 1, 0. So to speak, multiplied with +1. So this is an eigenstate of sigma z with eigenvalue +1. If you apply it to the 0, 1 state, you get -1. And then the notation is that we like to call the 1, 0 state that gives us +1. We call this the up state in such a ket notation. And the 0, 1, we will call this the down state. And it is understood that the up and the down always refer, therefore, to the z basis. Okay, so that's sigma z. We can also ask for eigenstates for any of the other operators, for example, sigma x. And so you can check for yourself that sigma x applied to 1, 1 is actually the same. And sigma x applied to 1, -1 gives me a minus sign. And so that is obviously then an eigenstate of the sigma x operator for +1. And sometimes people like to write it like this. So now this arrow is no longer pointing up and down in the z direction, but pointing right or left in the x direction. So that would be this state. I need some normalization, so I want to divide by the square root of the of Pythagoras, the 1 squared plus 1 squared. And I can also write it in terms of my up and down z basis. So it's, so to speak, up plus down, yeah, because it's just the same entries here. And likewise here, I can have the eigenstate of the sigma x pointing in the other direction. So I take that to be -1, pointing to the left means -1 for me. That would be, well, as we said, 1 -1, and again, normalization. I can also write it in terms of the z basis, like this. So that's the way to deal with these operators, and there's a little exercise you can try to find the eigenstates of sigma y if you don't already know them. Now, there's much more to say. I cannot possibly say everything, but one good thing is to know how to visualize spins, especially spin 1/2. And so what one can do is one can calculate the expectation value in a given state of the sigma spin vector operator. So more precisely, what I mean by that is, like for any expectation value, I have my wave function from the left and from the right. And sigma vector is really the vector that has sigma x, sigma y, and sigma z as entries. So these are operators as entries. And so, okay, taking the expectation value of this means taking the expectation value for each of the components. And what you get out, it turns out, is a vector that's always a unit vector. Yeah, so that's always a unit vector. And so it can be visualized. I can plot sigma z, say, in this direction, sigma x in that direction, and the expectation value of sigma y in that direction. And I will find, if I do this for an arbitrary state, I will find a unit vector pointing to some point. Now, if I change my state, I will still always get a unit vector. So all the possible points that I can get lie on the surface of the unit sphere. Let me see whether I can draw this in a nice way. Okay, so this is maybe not the best unit sphere. Well, okay, you can imagine. Okay, that's supposed to be a sphere. All permissible points lie on the surface of this unit sphere, and that's the so-called Bloch sphere. This is the Bloch vector lying on the surface of the Bloch sphere. Because this was first discussed, say, in terms of real electron spins. Okay. Now, is it analog of the Poincaré sphere? Yes, I believe so. So this kind of thing has been reinvented several times. So, for example, if you look into the polarization of classical electromagnetic waves, then you can draw a similar thing, and that's called then the Stokes sphere. So yes, this has been reinvented several times. Okay, so there's one question we can ask. Okay, so here's another question. Could we entangle two variables in the same particle instead of two particles? If not, how do we know which physical states we can prepare? That's a very good question. The answer is yes. I mean, a very simple example of what you have in mind is if I consider a particle not in one dimension, but say moving in two dimensions, then this one particle will have x1 and x2. And then I can play exactly the same tricks as before. And yes, I can produce an entangled state. The only little problem for our conceptual discussions with this approach is that I will never be able to somehow separate x1 and x2 because they are belonging to the same particle. So I will never be able with confidence to state that whatever I do on x2 cannot influence x1 because they belong to the same particle. So that's the only catch. But formally, yes, absolutely, you can entangle two variables in the same particle. Okay. So now, in the following, we sometimes need to measure, say, a spin not along x or y or z. Nature has more directions. We want to measure along an arbitrary direction. So formally, we can consider the projection of the spin vector onto an arbitrary direction. And so, well, you basically can treat your spin vector like you would treat a classical vector that points in some direction. And if you want to know how much of it points along a certain direction, well, you should probably take the scalar product, the projection along this direction. And the direction would be specified by a unit vector. So n is the direction in which you're interested. If n is the unit vector in z direction, then of course you will recover as z and so on, but it could be arbitrary. Now, S itself is h bar half times sigma, so we can also write it like this, which will make our life a little bit easier. And then we should investigate this object. So n times sigma, what is it? Yeah? And what I want to investigate is, in particular, its length. So I want to square this, and we will see something funny. So now, first I need to carry out the scalar product. It's just formally done like in classical, with classical vectors, only that the entries of sigma are now operators. And now I can square this, and of course there will be many terms. And I will arrive at terms like sigma x squared. Now what is this? Well, you can work it out for yourself, but it turns out this is just the identity matrix. Then there will be other terms like sigma x times sigma y, and there will be a corresponding term, sigma y times sigma x, and so on. Now, this again, you can calculate for yourself, and you will find, oh, this actually happens to be 0. And so then, in total, only these terms with the identity survive, and that's nx squared plus ny squared plus nz squared, and that's n vector squared. And since n was a unit vector, that's actually 1. So to be really more precise, this is all still an operator, so the identity operator. And so the 1 here is also really the identity. How can we project a spin in real space if it is not defined in real space? Well, okay, so first of all, what I'm saying here, you can take it if you want just as a formal exercise at the moment. But in the end, of course, it will be defined in real space. I mean, you are right in the sense that sometimes we are dealing with two-level systems, maybe introducing the Pauli matrices to deal with them, but they have a very abstract meaning. And it would be stupid to say that X, Y, Z have any relation to the real space axis. Okay, but if we are dealing really with a physical particle like an electron or so, then just similar to the angular momentum, the orbital angular momentum of the electron, we can define, if we choose, we can define it with respect to real space, and we should do so because we know specifically for the electron or any charged particle that has a spin, that there will be a magnetic moment connected to it that is parallel to the spin. And this magnetic moment then can be measured in real space. And for example, I could apply a magnetic field along the z direction, and then I want that the magnetic moment and therefore the spin is also pulled along the z direction. And it's at this point when I write down the interactions with fields that are defined in real space that I really have to, then I have to make sure that I know what I'm talking about, and then I should better choose my coordinate system for my spin in a consistent way so that it's aligned with the coordinate system of real space. Okay, so that was a long answer, but maybe I made it clear, because there are other more abstract spins like isospin, yeah, for neutrons and protons that really, where really they have no concrete meaning, and it would be pointless to say X, Y, Z have something to do with real space. Okay, but for now, you can also view this as a formal matter. So what we have learned is that this operator, n sigma, if it squares to the identity, then the only eigenvalues it can have are 1 and -1, just formally, yeah? Because if the square of think of it as a matrix, if the square of a matrix is just the identity matrix with only 1s on the diagonal, then before I squared, I could have only +1 or -1 on the diagonal. Now, this is, of course, all consistent. For example, if n equals the z direction, I get sigma z, and we already know it has eigenvalues plus minus 1. Also, sigma x actually had eigenvalues plus minus 1, so this is all not an accident. It is as it has to be. Okay. So now, maybe one little final little remark before we go on to 2 spins. One can also rotate spins. And here, I don't want to go too much into the details because calculations may be lengthy. I just want to say that this is probably something to read up in the textbook. I can rotate a spin by an arbitrary axis. So let's say psi is a spin 1/2 wave function. I can rotate the spin by an arbitrary axis if I take the spin operator, take its scalar product with suitable vector that defines the rotation axis and the rotation angle, and then take it to the exponent in this manner. So, okay, there are several things to say. So first, phi points along the rotation axis that I want to rotate around. And then the magnitude of phi is the rotation angle. What else to say? Well, this is a unitary operator, which it should be, because it should map the old state to a valid new state, which again has norm 1 if the old state had norm 1. So this has to be a unitary operator. So this is the simple way to rotate around an arbitrary axis. That's good. That will come in handy later. Now this is true even for arbitrary spin, but especially for spin 1/2, which is the case which we are most interested in. This rotation operator, say around the z-axis, if I work it out, insert simply, then I will only have the sigma z component, of course, because I'm rotating around the z-axis, so phi points along z. And then I have just the angle phi here. And the funny thing is, you can still work this out, even though it's an exponential of an operator. If you expand it in a Taylor series, you will see a pattern. The pattern is that whenever you square the sigma z, it becomes 1. So all the even powers will be the identity matrix 1, and the odd powers will be sigma z. So in total, if you sum all the terms afterwards, you will find it's the identity times cosine phi half, and then minus I sine phi half times sigma z. So these are the only 2 terms that you get. And so it's relatively easy to apply this, and it's very useful, actually. One little thing on the side, which you can see here, if you make a full rotation, phi equals 2 pi, you don't get back to exactly the same state, you get a -1. So this operator becomes a -1. And this can actually be measured in interference experiments if you compare it against another phase of a spin that you didn't rotate. And so that's just a funny fact about spin 1/2. Okay, so now 2 spin 1/2. Because that's what we need to understand the EPR experiment. Well, if we have 2 particles, then we have a product Hilbert space, formally speaking. So H1 times H2. And we can work out a product basis. So for example, we take for each particle, we take the Z basis, and then, for example, you have basis states like this one. So particle 1 is up, particle 2 is down. Sometimes I will abbreviate things like up, down, and it's clear which is which particle by the order. And then I can also apply operators. For example, I can apply the Z component of the spin operator for particle 2. I can apply that to any state, but for example, I can apply it to this particular state. And then what do I get? Well, it's particle 2, it's pointing down. So I get minus h bar half. And otherwise I reproduce the state. Okay. So now I can also consider the total spin. No one prevents me from this. So the total spin operator is just the sum of both spin operators. I can square that if I like, the old trick that we already did before. And then I can look at what are the eigenvalues, and especially what are the eigenstates for this total spin operator. But there is a question. Where can I find more info about rotation spin around an arbitrary axis? I think any beginner textbook on quantum physics should do the job. I don't have any particular one to recommend. So maybe someone else can chime in. So what are the so in particular, this operator for 2 spin 1/2 can have eigenvalue 0. And what's the eigenstate for eigenvalue 0? Such that if I apply S to that state, I get 0. Well, it turns out there's only a single such state, and it's the one we already know. Oops, it's the singlet state. It's called the singlet state because there is only a single such state. If I had asked for the eigenvalue 1, or 1 times h half, sorry, 1 times h bar. If I had asked for that eigenvalue, I would have found 3 states, and then that's called the triplet because there are 3 of them. Okay, but we only need the singlet. And now the funny thing is, because it's an eigenstate for eigenvalue 0, if I apply S to this state, I get 0 times the state, but I just get 0. And so now the funny thing is, what happens if I apply the rotation operator in an arbitrary, around an arbitrary axis to this particular state? Well, the way quantum physics or the operators work is, if I take the exponential of some operator, and this operator and the state I act on happens to be an eigenstate, then I can also replace the operator by its eigenvalue. The eigenvalue in this case, however, happens to be 0. So I get exponential of 0. You know what that is? That is 1. So I actually get the same state back. So that's very funny. I can rotate around an arbitrary axis by an arbitrary amount. I always get back the same old state. So the singlet state is rotationally invariant. So it's a very beautiful, very highly symmetric state. And it's very useful for what we are going to do. Okay. So now this is already nice. Now we can come back a little bit more to our situation. We can, for example, ask, okay, what about measurements? What if I measure not the z direction? We already discussed this. So measure the z direction of spin 1, you will find up or down with 50-50. And then measure spin 2, and that's anti-correlated. So it's down if the first one was up and so on. But now let's get more ambitious and let's say, let's measure along the x direction. Now, the funny thing is, I already gave you a hint what will happen when I proved to you that this state is rotationally invariant. So that should mean that if instead of measuring z on both sides, I measure x, I will find the same story actually. I will find that if the sx on particle 1 points to the right, the sx on particle 2 must point to the left. But let's see whether that's true, just by direct calculation. So we want to measure Sx and want to find out what happens, just as a little exercise, and then we can go further. Well, we know the eigenstates. The eigenstates are this one for the X operator and this one. Now, so in order to answer this question, what happens if I measure Sx? It would be very smart if we re-express our singlet state in terms of the X basis. So either this, or so there are actually two possibilities. Either I keep my singlet state in the Z basis as I wrote it initially, but then I should use these expressions to also convert back what I want to measure in terms of the Z basis, or I can rewrite my singlet state in terms of the X basis, and this would be a little exercise. But what you find is simply that this is exactly the same story as for the Z basis, only now reformulated in terms of the X eigenbasis. So that's of course something we already anticipate because we have proven that it's rotationally invariant. And so if you now do a measurement, say, of particle 1 in the X basis, you get either, well, +1 or -1. And depending on what you, oopsie, sorry, I did a mistake. This would not be a singlet state. It should be exactly like the story for Z. So they should be exactly opposite to each other. And this is then also what you would find in a measurement. So for example, if you measure Sx and find with 50% probability the one of the two eigenstates, then by necessity the second one will just point in the opposite direction. Yeah, thank you for pointing this out. Okay, so this is how we can do these things. So as I said, until next time we will prepare a few exercises, among them also some exercise about the spin physics that you can work out. You could, for example, look into how this is rewritten in the Y basis, things like this. What we will then also discuss finally is how does it work with Bell's inequalities? How did Bell arrive at his original Bell's inequalities? And again, he started from the same question that also EPR started from, namely, can we actually find an underlying theory below quantum mechanics? And in his case, he was even very modest. He said, can I find an underlying theory, not for all of quantum mechanics, but only for the particular EPR experiment in the spin version that we discussed? Yeah? So that is something that we will discuss next time, but we can already draw a little figure. Can we find an explanation, a simple-minded, classical-looking explanation without quantum mechanical mysteries that would reproduce the measurement results that quantum mechanics predicts for this particular version of the EPR experiment, for the 2-spin 1/2 in the singlet state, where in particular, if I measure one along one axis, I automatically can be sure that I will find the other one pointing in the opposite direction. So here's a question. Both original version and the Bohm version of EPR rely on conservation laws. The former on momentum conservation and the latter on spin conservation. I would not necessarily say that they rely on conservation laws. Now, it's true that, let's go back. Oopsie. It's true that if I want to produce an EPR wave function for this position momentum version, then one way to do it, so to speak, is to have a molecule fragment and the different fragments fly off into different directions, and there will be momentum conservation and center of mass conservation involved in there. I know a little bit less about the spin version, what you mean there with conservation law, but I can guarantee you that we will ultimately find when we abstract away all these simple examples that people started out from, that there is nothing special about conservation laws. All you need is these entangled states. Not all entangled states will work under all circumstances, but you need such entangled states, and many of them will work, and then you can derive Bell inequalities. Okay. Question concerning the exam. Okay, good. We don't have any exercise up to now, so what's the best way to prepare for the exam? Well, you get the exercises. So that's one of the reasons why we are then providing you with exercises. So the way I think about this is, say, maybe 4 or 5 times during the semester, we will give you 2-3 exercises, and we will put them on the website, and we will offer to discuss them, and this is how you prepare for the exam. Okay, any more questions for right now? Well, if not, I just want to remind you that we have this really nice discussion group. There's not yet much activity there, but I already saw someone worked out a nice little program to get the statistics of this Merman Gedanken experiment and put it there. So I encourage you to discuss in this discussion group. It's linked from the website that we have. Okay, so then see you next time. Okay, so there was still one question, but maybe I can explain that next time, the spooky action at a distance. So we can repeat it at the beginning. Okay, very good.